Welcome to Lecture 2 of DIY Transcriptomics. In this lecture, we'll actually get down to the business of mapping raw sequencing reads from our FASTQ files to a reference transcriptome to produce numeric gene expression data. And we'll do that using Callisto. Now remember, Callisto is just one piece of command line software that we installed in the last lecture. So if you haven't done that yet, you need to go back to Lecture 1 and make sure you can get through that installation process without any problems. In addition to the raw sequencing data itself, we also discussed how FASTQ files contain information encoded in these ASC2 characters that tell us about the quality of each base that was sequenced. One of the things we'll do in this lecture is actually use one of the programs we installed in the last lecture, FastQC, to parse these FASTQ files, and in particular, the quality scores, so that we can understand the quality of the sequencing data before we move forward with any downstream analysis. Okay, before we jump in, let's just take stock of where we are at this very early stage in the course. First of all, everyone should have the most current version of R, RStudio, and Bioconductor installed on their laptops. You should understand what these three pieces of software are and how they're distinct from each other. And I also ask that if you happen to have any of these pieces of software already installed on your laptop prior to starting this course, that you still move through that installation process with me that we detailed in Lecture 1 so that we're all working with the most current version and the same version throughout the course. You should have a basic understanding of the RStudio interface and the notion of R packages, something we'll be spending a lot of time talking about and working with throughout this course. You should know how to open your terminal if you're on a Mac, or the command prompt or related applications if you're on a Windows machine. And you should also have a code-aware text editor installed, and I suggested either Sublime or Visual Studio Code or both. Everyone should have Miniconda 3 installed on their laptop, and you would have used this software, Miniconda, to create at least one Conda environment that contained at least Callisto. Now, this notion of using Conda to create Conda environments was really central in the first lecture, and it's going to be really important in this lecture because we'll be firing up one of those Conda environments to actually access the software that we'll use for doing our RNA-seq read mapping. And so I want to take just a minute to talk about Conda and hopefully what we've all accomplished with respect to creating environments. When we installed Miniconda 3, we got a base environment for free, if you will. And then in Lecture 1, we created 4 different unique environments. Remember, each of these is a bit like a silo or a bin that we can put software into. Sometimes one piece of software, sometimes multiple pieces of software. Now, in an ideal world, we could just put all of our software in one place on our computer and we would never have to create these environments. But if we did that, it wouldn't be long into that installation process before the bits and pieces or the dependencies that, say, Callisto needed in order to properly run were in direct conflict with the bits and pieces or dependencies that something like SourMash or Centrifuge or even MultiQC would need. And so those dependency conflicts were the source of, and still to some extent are the source of, a lot of headaches in installing command line programs. And the real advantage of Conda is that it helps manage those dependencies and those conflicts for you and makes that installation process much more simple. So we created these 4 environments, one of which we called RNA-seq, and that RNA-seq environment contained 3 pieces of software if you're able to get through that whole installation process: Callisto, FastQC, and MultiQC. Now I have an asterisk here next to FastQC because if you had any problems installing FastQC, there are other programs that achieve the same effect, that is checking the quality of raw sequencing files, and one really good one is FastP for FastQ preprocessing software. And so you could install FastP in the same way essentially that we installed FastQC, and I've added those instructions to the protocols page that I showed you in the last lecture. In fact, if you want to give both of these pieces of software a try, both FastP and FastQC, you could put them both inside this RNA-seq environment. We also created an environment we called KB, and that had a single piece of software, KB Python, that we'll use at the end of the course for doing single-cell seq work, and KB Python is great for pre-processing single-cell sequencing data. And then we created 2 additional environments, each with a single piece of software, SourMash and Centrifuge. And those environments and those pieces of software are really probably most well known for being tools that are useful for handling shotgun metagenomic data, but we'll actually use them in this course to try to interrogate the complexity of our samples and understand if there's any non-human sequencing reads in the data that we're working with. Now, I also cautioned everyone to be careful where they were installing software and to not accidentally put a bunch of software in our base environment. In general, we try to be careful not to pollute that base environment by installing a whole bunch of stuff in it. If we mess up one of these environments, it's easy to just delete it and get rid of it and start again. All right. Remember that in order to access a piece of software in one of these silos or environments, we have to first activate the environment and then run the program. So it's a two-step process. And to activate the environment, we would run conda, activate, and then call the environment by name. In this case, RNA-seq or KB. Now, you could have named these environments whatever you wanted, but hopefully you've named them the same thing I have so that it's easier to follow these instructions. Once you've activated the environment, you're going to see that environment name appear in parentheses at the command line prompt, and then you can call the program you want to use. So if I want to run Callisto to do read mapping, I would first say conda activate RNA-seq, and then I could run Callisto by just typing Callisto. Now that that's out of the way, we're ready to talk about what we need to accomplish in today's lecture. So if you head on over to the course website and you click on the lecture card for today, we'll all be looking at that same lecture page. And this is just a good opportunity to remind everyone that if you want to follow along with my slides, you can click on the link at the top of that lecture page. Okay, let's talk about learning objectives. We need to talk about the course data set, what it is, how you get it, where it comes from. This is really important because it's the data set that we'll all be using throughout the majority of the rest of the course. At the end of the course, we'll have to switch to a different data set for our single-cell RNA sequencing work, but this data set is the one that we'll be using for months to come. You also need to download and examine a reference, your first reference file, which is going to be a reference transcriptome that we'll get from Ensemble. And this is going to be great practice because it'll be the same way you get any reference file for any sort of genomic work moving forward. We'll then fire up that RNA-seq conda environment and use Callisto to turn this reference transcriptome into a form that's more searchable, called an index. We'll then turn back to Callisto to then map our raw reads to the index that we just created. And while we're doing that, while that's running, we'll have a chance to take a step back and talk about what's happening, really. How was that index constructed and how does it facilitate read alignment? We'll also have a chance to pop the hood on Callisto a little bit and talk about how Callisto and tools like it have really enabled this kind of extremely rapid read mapping to be carried out on our laptop. I have to confess that today's lecture, perhaps more than any other in the course, is going to look and feel a lot like a baking show. And what I mean by that is I'm going to present you with a recipe for carrying out read mapping. And we're going to follow that recipe together. I'm going to mix the ingredients right in front of you. I'm going to put everything together, put it in the oven, but I'm going to pull out a cake that I've actually already baked because we don't have time to wait for that baking process to finish in the course of this video. And what I'm going to ask you to do is to go home with that recipe and those ingredients and mix them together yourself and actually bake the cake. And just like following any recipe, there's things that might surprise you from just having watched me do it, how long something takes or how things sort of come together. But in the end, you will end up with a cake, and hopefully by the end of this video lecture, we'll have something that looks really good that we've accomplished together. So let's talk about the course data set. If you navigate to the course website and you click on the data tab at the menu at the top, you'll be taken to a page that describes the course data set and gives you access to downloading it. So this is a data set that comes from a collaboration between my lab, the laboratory of Phil Scott, also here at Penn, and our colleagues in Salvador, Brazil. If you'd like to know more about this data and what we did with it, you can see the manuscript linked here. This is an RNA-seq data set from skin biopsies collected from human patients that had a disease called cutaneous leishmaniasis. This disease is a parasitic disease. It's endemic in South America and in other regions of the world. It's a neglected tropical disease, which means it receives very little attention and funding. And the data that you'll be working with comes from 5 patients that have cutaneous leishmaniasis and 5 healthy endemic controls. This disease is caused when an infected sandfly bites an individual and deposits parasites into the skin. And what happens after that is a lesion or ulcer, oftentimes quite large, develops at the site of infection. And generally, we're interested in how the immune system might play a role in the development of that pathology, that skin pathology. As I mentioned at the beginning of the course in the welcome lecture, we always try to give people multiple on-ramps or entry points for starting an analysis. And so the first on-ramp to getting this data is option 1, which is described a little lower down on this page. This is the preferred option. This is the option that I'll be using. And that's simply to download the raw FASTQ files. And I provide a link to do that here on the data page. You'll need about 30 gigs of storage space on your hard drive to accommodate these 10 FASTQ files. That's quite a bit of space, but if you remember, I asked you to kind of do a little housekeeping with your laptop and clear off unnecessary files, and it was precisely for this reason, because we need to accommodate this data set and others later in the course. Now, I just want to urge you not to uncompress or double-click these files. They are gzipped or .gz files. They're compressed. And so double-clicking them or decompressing them will result in data that's much larger than just 30 gigs. So leave them as .gz files. All the programs we use will work with the files in that zipped format. So we don't actually need to unzip them at all. There's also a link to 2 other files here that are going to be really important later in the course, especially once we get into R, a study design file, for example, and a shell script that we'll deal with or talk about in this week's lab, but you will not need those for this lecture. And so you can download them now or you can leave them until later. Now, perhaps you don't have 30 gigs of storage space on your hard drive, or maybe in the process of moving through today's lecture, your computer really struggles to do these read mappings, even with Callisto. And so in that case, the second on-ramp we provide is for you to download the data after we've already mapped it, so bypassing that Callisto step altogether. And so we've already mapped those data for you. They're available here to download as a set of 10 folders. And all the associated output files. And since the outputs from Callisto are flat text files that summarize read mapping as numeric data, these files are far, far smaller than the raw FASTQ files. And so there's no reason why anyone would not be able to store these output files on their computer. So option 1 is preferred. And if that works for you, you don't even need to worry about option 2. But if you're struggling with option 1 or struggling to do the read mappings in this video, then option 2 might be for you. Either way, you will be able to carry forward with the remainder of the course, and you'll also have an understanding of how Callisto works and how to use it. Now, we've already discussed that our FASTQ files have quality scores encoded in them using these ASC2 characters for efficiency, and that as our sequencing run progresses with cycle number moving up from left to right, the percentage of bases that have a Q or quality score greater than 30 begins to decline. And the rate at which the quality scores declines and the overall quality across the full length of the read varies a lot depending on your particular experiment, sequencing platform, and many other parameters. And so suffice it to say, it's really critical that you assess the quality of your raw data before you move forward with any subsequent downstream analysis. Now, frankly, one of the easiest ways to access or understand quality information about your sequencing run is to actually just watch the run itself. Most Illumina sequencers produce this sort of dashboard of quality metrics as the run is progressing. So we get a quality score distribution graph, we get a heat map that shows quality scores as the run progresses. We get information about not just the quality of the reads, but the quantity of reads produced, and much, much more across these different tabs. And if we don't happen to be standing in front of the sequencer, that's okay. We can often access that data directly on Illumina's BaseSpace cloud service, because all of this quality data is streamed in real time to BaseSpace. But we aren't always standing right in front of the machine, and we don't always have access to BaseSpace. Maybe we downloaded our data from a core facility, Or maybe we got data from the sequence read archive. In both of those cases, the quality data in this summarized form does not come along with it, but we know that it's embedded inside the FASTQ files itself. In order to extract that quality information that's embedded in the FASTQ files, we're going to use a piece of software called FastQC. This is one of the command line tools that we installed in the last lecture, and we actually installed it in that RNA-seq Conda environment along with Callisto and MultiQC. If you want to read more about FastQC, I'd encourage you to check out their website, which I linked to here. But for our purposes, one of the great things about it is it's really easy to run. You just simply call the name of the program when you're at the command line and point it to a FASTQ file. Now, we installed FastQC in that Conda environment, so we have to first activate the Conda environment by saying conda activate RNA-seq, and then we can access FastQC. This program works on compressed or gzipped files, so that's great. And we don't need to process one file at a time. We can take advantage of the handy asterisk or wildcard character, which tells FastQC, and in fact many other programs, process any file that ends in .gz. It can have anything else prior to this. It could say sample1 or sample2 or my favorite sample. FastQC doesn't care. Anything followed by .gz. Now, it also can take advantage of something called multi-threading. Remember, my computer, and yours as well, most likely, has more than one hardware core. In this case, mine has 4 cores. And FastQC, like many programs, can take advantage of your hardware configuration of multiple cores and can spread the job out across those cores. For every physical core you have 2 virtual cores, also known as threads. And so we can modify this command slightly to say FastQC, process any of the gzipped files on my folder, and do that across 8 threads. So -T8 says use all 8 threads or 4 physical cores. If your machine has 2 cores, then you would say -T4 because 2 cores, 2 physical cores is 4 threads. Now, for those of you that installed FastP instead of or in addition to FastQC, it's also really easy to run. Again, you just call the program by name and you point it to a FastQ file. It can accept zipped FastQ files, but we do have to tell FastP that that's an input file. So it wants a -I parameter or argument, as we call it. So FastP -I for input and then the name of the FastQ file. And it can also take advantage of multi-threading. We can say FastP -I, here's a sample, and process that using all 8 threads. And of course, we can use that wildcard character to process many samples. Now, one great thing about FastP that's different than FastQC is it has additional arguments or parameters that we can specify that will actually take this input file and not just assess the quality, but also take it through a series of trimming and filtering steps and produce an output FastQ file that now has been quality checked and trimmed and filtered. We're not going to cover that in this lecture, so if you're interested in that, I'd encourage you to check out the original paper and the GitHub repository for FastP so that you understand how that works. Okay, great. So we are now ready to demo both FastQC and FastP using the course dataset. Now, remember, both programs live inside of that RNA-seq Conda environment that we set up. And so that means we have to first activate that Conda environment to use either program. So with that in mind, I'm going to head over to my terminal. If you're on a Windows machine, this would be perhaps your command prompt application. And I can see right off the bat that I am sitting in that base Conda environment. That's the one that was set up for us by default when we installed Miniconda 3. So I need to move by saying conda activate into the RNA-seq environment. And I can see that I successfully did that. I moved from base to RNA-seq. I'm ready to go, except we have to know where our data lives, right? We want to run FastQC or FastP on our data, which means we need to be in the right place on our computer. Now, I know where I downloaded my data, but you also need to know where you downloaded yours, and they might be different places. I downloaded my data into a folder called course_dataset that lives on my desktop. So I now need to move into that folder, and I'll do that using the cd command for change directory. I'll say cd desktop and course dataset. Now, I was able to type those so quickly because you can actually just type the first few characters of a file name or folder and then hit tab, and your operating system will just auto-complete. So it makes it really easy. I hit enter and I can see that I successfully moved from my home directory, which is signified or symbolized by a tilde, into the course dataset folder. Perfect. And if I hit ls for list, I'll be able to list the contents of that directory or folder, and I can see all the files here, which will match what I see when I open up that folder by double clicking it. Just quickly, 10 files, each a FASTQ file zipped up, one from each patient, 5 endemic normals, and 5 patients with cutaneous leishmaniasis. And then an 11th file, and this is where that cooking element comes in, is that that file is a 1 million subsample from this file. And that's useful because it makes the file much smaller and much easier and faster for me to work with in this demonstration. So I'm going to demonstrate on this trimmed down file, but I'm going to ask that you repeat this process with the actual real files here. Also note that these files are pretty big, upwards of almost 6 gigs, except one of them is much smaller, on an order of magnitude smaller than the others. So we'll have a chance to ask whether that actually impacts or has any impact on the quality of data in that file. And then of course, the file I'll be demonstrating on is much, much smaller. Great. So now that I'm in the right place and I see those files, I can run FastQC. I just type the program, I point it to a file, so I'm just going to point it to this one trimmed down file. So I just copied that name and I pasted it. And then I know that my computer has 4 cores, and I know that that is the equivalent of 8 threads. So I can multi-thread this to make it really fast and hit enter. And here it is running through the analysis of that file and updating me on the progress. And just like that, it's done. And I can see that after completing, it's generated 2 files. And I know these came from FastQC because they actually have FastQC in the name. One's a zipped up folder that has all the raw output data from FastQC, but that's all nicely summarized in that HTML file here. And that HTML file can just be opened in a web browser to really view all of the data from FastQC. Before I do that, I'm going to go ahead and run FastP as well. So I just say FastP, the input file, so the same file, and again, I can multi-thread that. And it's going to run just as quickly. It gives it a little bit of a different output. It's not going to update my progress as it moves through. It just finishes. And it too generated 2 files, a log file in the form of a JSON formatted file, and then an HTML, just like FastQC did. So now I have 2 HTML files, one for each program, and I can now open one of those files and it will launch in my web browser and be ready to look at. Let's go ahead and open the FastQC HTML file. I'll just double click that and it opens right in my web browser. And right away I'm greeted with a pretty familiar plot by this point, one that shows my quality scores on the y-axis by read position or base position on the x-axis. And I can see that this particular subsampled file has high quality, over 30. So in this green zone, all along the full length of the read. But I get far more than this plot. I can scroll down and see lots of other plots and statistics, and I can navigate that whole page using this index on the left-hand side. I just want to point out that FastQC tries, but oftentimes fails to report or interpret these statistics and plots. You can see that here on the left-hand side. So it's flagged many of these as being good or passing some metric, while others have a yellow warning with an exclamation, and still others have this concerning red X for failing. FastQC knows nothing of the kind of experiment we ran. They don't know if we did RNA-seq or ChIP-seq or genome sequencing. And they make some fundamental assumptions about the kind of data that we're working with that can just frankly be wrong. So if we click on sequence duplication levels, it's a good example of what I'm talking about. We can see the percentage of total sequences that have been duplicated some level, over 10 times, over 100 or over 1,000. I see these peaks in percentage of sequences that have been duplicated those number of times. And that might be concerning, but if you're doing RNA-seq, it's reassuring to see duplication. We're expecting some genes in the transcriptome to be highly expressed and therefore to have a number of repeated or duplicate sequences. So just because these are flagged as warning or failing should not necessarily in and of itself concern you. All right, if I go back to my working directory, I can open the fastp file. Again, if you happen to run fastp, you didn't have to. But again, we see a bunch of summary statistics here. In the case of fastp, we see some before filtering statistics and then after filtering. We didn't actually use fastp to filter, so these are identical. But if you had used fastp to filter, if you choose to explore that, then you would get those pre and post filtering metrics here. We see a similar quality plot, and again, more and more graphs that I won't get into here, but that you can certainly explore more on your own. And that's really all there is to using FastQC and FastP. You can see they're both really easy to use. They're used in a very similar way. So if you know how to use one, you know how to use the other. And so you're ready now to use one or both of those programs on the real FastQ files. It will take longer than I just demonstrated for the subsampled file, but they still will complete in several minutes on your own data. And that's it. Go ahead and get to work. In the next video, we're going to tackle actually doing the alignments.